Scientists call it dark energy, and it makes up 70% of everything that exists. We are living in a cosmic ocean where islands of matter are drifting apart, never to reunite. You will journey through voids so massive they should not exist, discover why we see no alien civilizations, and learn what waits at the end of time. If you are ready to see how terrifying emptiness truly is, hit that like button and subscribe. Brace yourselves. We descend into the void. Look around you. Everything you see, everything you touch, every person you know exists because of matter. Your body, this planet, every star burning in the night sky. But here is what scientists confirmed through decades of observation. All of that combined makes up less than 1% of the universe. The rest is void. Imagine taking every galaxy we can observe, every billion stars they contain, every planet orbiting those stars, and crushing them together. You would fill less than a trillionth of the space that exists. The average density of the universe is roughly 6 hydrogen atoms per cubic meter. Walk into an empty room, and you are breathing in billions more particles than what fills the same volume in deep space. This emptiness is not random. Measurements from the Planck satellite and Hubble Space Telescope reveal that matter clusters in thin filaments and walls, like a cosmic web. Between these structures stretch regions so empty they make the space between stars look crowded. Astronomers call them voids, and they dominate everything. Think of the universe as an ocean. Galaxies are not scattered evenly like salt dissolved in water. They gather in tiny foam bubbles floating on the surface, while massive bubbles of nothing sit underneath. You live inside one of those foam specks, surrounded by darkness so complete it swallows light. Why does this matter to you? Because the emptiness is growing. Every second, space itself expands, pushing those bubbles of nothing wider. The galaxy clusters sitting at the edges of voids are accelerating away from each other, driven by a force we barely understand. That force is called dark energy, and it fills the void with something stranger than empty space. Scientists measuring distant supernovae discovered in 1998 that expansion is speeding up. This was not supposed to happen. Gravity should slow everything down, pulling matter back together. Instead, something in the void is overpowering gravity itself. The emptier a region becomes, the stronger this force grows. You exist in a brief window where stars still shine and galaxies cluster close enough to see, but the void is winning. With every passing moment, more space opens between islands of matter. Eventually, the darkness will separate everything so completely that entire galaxies will vanish beyond reach, swallowed by expanding nothingness. What lives in that void is still a mystery. What we know for certain is this: emptiness is not passive. It is active, aggressive, and spreading. But the true scale of this void is something you cannot imagine yet. The largest structures we can map are not clusters of galaxies. They are the empty spaces between them. In 2004, astronomers completed the Sloan Digital Sky Survey, a project that mapped over 1 million galaxies across billions of light-years. What they found defied expectations. Galaxies formed thin threads and sheets surrounding enormous bubbles of almost pure vacuum. Some of these bubbles measured over 1 billion light-years across. To cross one of these voids at light speed would take longer than Earth has existed. Light that began its journey when dinosaurs walked this planet would still be crossing empty darkness today. These are not small gaps between neighborhoods. These are chasms that separate entire regions of the cosmos. Inside a typical void, you would find perhaps one galaxy per every 10 million cubic light-years. Compare that to our local neighborhood, where dozens of galaxies crowd within a few million light-years. The difference is staggering. You could fit millions of galaxy clusters inside a single void, yet most contain almost nothing. Scientists using supercomputers ran simulations of cosmic evolution. They started with the conditions moments after the Big Bang and let gravity do its work over billions of years. The simulations produced the same web-like pattern we observe. Matter naturally collapses into dense filaments while voids expand between them. This is confirmed science, validated by multiple independent studies. But here is where things become unsettling. The voids are growing faster than the simulations predicted. Dark energy is not just maintaining these empty regions. It is actively inflating them, pushing their walls outward at accelerating speeds. Measurements from the Dark Energy Survey show that voids expand roughly 10% faster than expected based on gravity alone. What does this mean for you? Every galaxy sitting on the edge of a void is being pulled in two directions. Gravity tries to keep it connected to nearby galaxies. Dark energy tries to drag it into isolation. Right now, gravity still wins in dense regions. But in the voids, dark energy dominates completely. Think about standing at the edge of an expanding chasm. The ground beneath neighboring towns is moving away, slowly at first, then faster. Eventually, the gap becomes too wide to cross. That is happening to galaxy clusters across the universe. The voids between them are becoming permanent barriers, dividing the cosmos into isolated kingdoms that will never communicate again. The emptiness is not waiting in some distant future. It is here, surrounding us, growing every moment, and one void in particular reveals just how extreme this emptiness can become. In 1981, astronomer Robert Kirshner discovered something that should not exist. While mapping galaxies in the constellation Bootes, his team found a region containing almost nothing. They searched the area repeatedly, using increasingly powerful telescopes. The result remained the same, a sphere of darkness measuring 330 million light-years across, nearly empty. Most cosmic voids contain sparse galaxies, scattered throughout. The Bootes void is different. In a region that should hold roughly 10,000 galaxies, scientists have found only 60. That is a 99.4% vacancy rate. If our galaxy existed in the center of this void, we would see almost no neighboring galaxies anywhere in the night sky, just darkness in every direction. Astronomers call it the Great Nothing. Some call it the supervoid. Its size alone violates what we thought possible. According to standard cosmological models, structures this empty should be incredibly rare. The universe has not existed long enough for gravity to evacuate such a massive region completely. Yet there it sits, confirmed by multiple surveys, including data from the 2-degree field galaxy redshift survey. What could create such emptiness? One theory suggests the void formed from an unusually low-density region in the early universe. As expansion continued, dark energy pushed matter away faster than gravity could pull it back. Over billions of years, the void inflated, while galaxies fled to its edges. Computer simulations show this is possible, though statistically unlikely. Another theory is more disturbing. Some physicists propose that voids this size could indicate variations in dark energy itself. If the force tearing space apart is stronger in certain regions, those areas would become empty faster. This would mean the universe is not uniform. Some neighborhoods face faster destruction than others. For anyone living in a galaxy inside the Bootes void, the night sky would appear almost alien. Instead of seeing thousands of distant galaxies through telescopes, they would observe perhaps a few dozen dim smudges. Their view of the universe would be fundamentally limited by the emptiness surrounding them. The Bootes void sits roughly 700 million light-years from Earth. We can observe it because light has had time to cross that distance. But as the void continues expanding, eventually even that light will struggle to reach us. The darkness will grow darker. Measurements show the void is expanding at the same rate as the rest of the universe, but its sheer emptiness makes it a preview of what waits for everything. Every galaxy cluster will eventually become an island in a void this vast. The Bootes void is not an anomaly, it is a warning, and the force creating these voids is something we are only beginning to understand. Something invisible fills the universe and wants to rip it to pieces. In 1998, 2 teams of astronomers studied distant supernovae to measure cosmic expansion. They expected to find that gravity was slowing everything down. Instead, their data showed the opposite. Expansion is accelerating. Galaxies farther away are moving faster than those nearby. This discovery earned the Nobel Prize in Physics because it revealed a force we never knew existed. Scientists named it dark energy. The name is a placeholder because we have no idea what it actually is. We just know what it does. It pushes space apart. Think of the universe as a balloon being inflated. Galaxies are dots drawn on the surface. As you blow air into the balloon, every dot moves away from every other dot. Now, imagine the balloon is inflating faster every second. That acceleration comes from dark energy. It makes up roughly 70% of the total mass and energy in existence. Yet we cannot see it, touch it, or directly detect it. We only see its effects. Here is what confirmed observations tell us. Dark energy behaves like a property of space itself. Create more space through expansion, and you create more dark energy. This means the force grows stronger over time. Early in the universe, when everything was compressed together, dark energy was weak, gravity dominated. But as space expanded and matter spread apart, dark energy gained control. Measurements from the Wilkinson microwave anisotropy probe mapped the cosmic microwave background, light from when the universe was only 380,000 years old. Those measurements, combined with supernova data, give us the current expansion rate. Space is stretching at roughly 46 miles per second for every 3 million light-years of distance. This rate increases the farther you look. What does this mean in practical terms? Pick two galaxies separated by 100 million light-years. Every second, the space between them grows by roughly 1,500 miles. They are not moving through space. Space itself is expanding, carrying them apart. Nothing they do can stop it. The terrifying part is how smoothly this happens. You cannot feel dark energy pulling you apart because gravity holds atoms, planets, and even galaxy clusters together. But cross into the voids between clusters, where gravity is weak and dark energy dominates completely. Those regions are expanding faster than anything inside them can resist. Some physicists theorize dark energy might change strength over time. If it grows more powerful, expansion could accelerate faster than predicted. If it weakens, the universe might slow down. Current evidence suggests it remains constant, which means the acceleration we see today will continue forever. Dark energy is not destroying matter directly, it is destroying proximity. Every structure in the universe will eventually become an isolated island surrounded by unreachable darkness, and the speed at which this isolation spreads is increasing. Stand still and measure the speed of a distant galaxy. Wait 1 billion years and measure again. It will be moving faster. This is not speculation. This is confirmed by observations stretching back decades. The Hubble Space Telescope tracked galaxies across cosmic history, measuring their velocities at different distances. The farther away a galaxy sits, the faster it recedes. But more importantly, galaxies at the same distance are moving faster now than they were in the past. The acceleration is relentless. Galaxy clusters sitting 10 billion light-years away are receding at roughly 90% the speed of light. Those farther still are moving even faster. Eventually, you reach a distance where expansion carries objects away faster than light itself can travel. This is called the cosmic event horizon. Once a galaxy crosses that horizon, its light can never reach us, ever. The space between us expands faster than photons can cross it. From our perspective, the galaxy effectively vanishes. It still exists, but we are permanently cut off from it. Any civilization living there could shine the brightest beacon imaginable, and we would never see it. Currently, the event horizon sits roughly 16 billion light-years away, but it is moving closer. As dark energy continues accelerating expansion, that boundary creeps toward us. Galaxies we can see today will cross it in the future. Our observable universe is shrinking. The local group, our cluster of galaxies, including the Milky Way, Andromeda, and roughly 50 smaller galaxies, is held together by gravity. We are safe for now, but look beyond our neighborhood, and the story changes. The Virgo supercluster, a collection of galaxy groups, including ours, is already beginning to stretch apart. Measurements show that galaxies on the far edge of Virgo are accelerating away faster than gravity can compensate. In approximately 100 billion years, every galaxy outside the local group will have crossed the event horizon. Our descendants, if any exist, will look into the night sky and see only the galaxies bound to us by gravity. The rest of the universe will be invisible, erased by expansion. But that assumes we survive what comes before. Because there is a reason we see no other civilizations racing against this cosmic clock. The universe has existed for 13.8 billion years. Stars have been forming for over 13 billion years. Planets orbited many of those stars, some in habitable zones where liquid water could exist. If intelligent life arises even rarely, the galaxy should be filled with civilizations, some millions of years older than us, some billions. We see nothing. No megastructures harvesting starlight. No radio signals carrying information across space. No signs of interstellar travel. No artificial satellites orbiting distant worlds. Silence. Complete silence. This is called the Fermi paradox, named after physicist Enrico Fermi, who asked a simple question: where is everybody? The Great Filter theory offers one explanation, and it is chilling. Somewhere between the formation of life and the colonization of galaxies, something stops civilizations from spreading, a barrier so deadly that no species crosses it. The filter could sit behind us. Maybe the jump from simple chemistry to self-replicating life is so improbable that Earth is the only place it happened. Maybe the evolution of intelligence is 1,000,000,000 to 1 fluke. If so, we are safe. We already passed the filter, or the filter sits ahead. Maybe civilizations inevitably develop technologies that destroy them. Nuclear weapons, biological engineering, artificial intelligence, or something we have not discovered yet. Maybe the window between achieving advanced technology and self-destruction is only a few centuries. Every intelligent species reaches this point, then vanishes. Consider the timescales involved. If a civilization survives for 1,000,000 years and spreads across the galaxy, they should still exist today. Stars live for billions of years. Even if civilizations rise and fall, some should be thriving right now. Yet we detect nothing. Some researchers argue the filter might be environmental. Climate change, resource depletion, or cosmic catastrophes like gamma-ray bursts could wipe out complex life before it spreads beyond one planet. Others suggest civilizations intentionally stay hidden, avoiding contact to prevent hostile encounters. But this seems unlikely. It would require every single civilization to follow the same policy forever. The mathematics of the Drake equation estimates billions of potential civilizations could exist in our galaxy alone. Yet, the emptiness persists. Either the equation is wrong, or something removes civilizations before they become visible. We launched the Voyager probes in 1977, carrying messages meant for alien civilizations. Decades later, we built the James Webb Space Telescope to search for biosignatures on distant planets. So far, nothing. We keep searching because the alternative is accepting we might be the only ones watching as the universe tears itself apart. If the great filter lies ahead, we are running out of time to find it. Dark energy guarantees that any future civilizations will inherit an even emptier cosmos, and the silence surrounding us suggests we might already be too late. 60 years of searching, thousands of scientists, billions of dollars invested in telescopes, satellites, and detection equipment. The result is the same: nothing. The search for extraterrestrial intelligence, known as SETI, began in 1960 when astronomer Frank Drake pointed a radio telescope at 2 nearby stars. He listened for signals that could only come from artificial sources. Regular pulses, mathematical sequences, anything showing design rather than randomness. He found cosmic noise. Since then, technology improved exponentially. We built arrays of radio dishes working together, scanning millions of channels simultaneously. Projects like Breakthrough Listen analyze data from the most powerful telescopes on Earth, searching for even the faintest hint of alien technology. They examine billions of signals every day. Every signal has a natural explanation. Pulsars, quasars, magnetars, cosmic background radiation. The universe produces countless sources of radio waves. So far, none show the signature of intelligence. Think about what this means. We can detect radio waves from galaxies billions of light years away. If an alien civilization built transmitters comparable to ours, we could detect them from thousands of light years. If they built something more powerful, deliberately trying to signal, we would see it across the galaxy. Yet we find nothing. The WOW signal, detected in 1977, remains the most promising candidate. It lasted 72 seconds, showed all the characteristics of an artificial signal, and never repeated. Scientists tried to find it again using more powerful equipment. It never reappeared. Most now believe it was an extremely rare natural phenomenon, or possibly even terrestrial interference. We have also searched for technosignatures, evidence of advanced technology altering stars or planets. A civilization needing massive energy might build structures around their star, collecting most of its light. This would create a specific dip in brightness we could detect. Surveys examined hundreds of thousands of stars. No confirmed Dyson spheres. No stellar engineering. No signs anyone has reshaped their solar system. The James Webb Space Telescope now analyzes the atmospheres of exoplanets, searching for industrial pollution or other chemical imbalances that natural processes could not create. Early results show nothing unusual. Oxygen and methane exist on some worlds, produced by natural chemistry. No chlorofluorocarbons. No signs of industry. Could civilizations exist but choose not to communicate? Possibly. But this would need to be universal. Every single species across billions of years would need to stay silent. It seems more likely that something prevents civilizations from reaching the stage where they could signal us. The galaxy is roughly 100,000 light-years across. Radio waves travel at light speed. A signal sent from the far side would take 100,000 years to reach us. Maybe civilizations rise and fall before their signals arrive. Maybe we are listening too early or too late. Or maybe we truly are alone in an expanding void that will only grow emptier. You exist on a planet orbiting an ordinary star in a galaxy containing roughly 400 billion stars. The observable universe holds approximately 2 trillion galaxies. Even conservative estimates suggest billions of planets could support life. So where is everyone? Enrico Fermi asked this question during a casual lunch conversation in 1950. His colleagues had been discussing flying saucers and the possibility of extraterrestrial visitors. Fermi did a quick mental calculation and concluded that if intelligent life were common, evidence should be everywhere. We should see signs in our own solar system, probes, artifacts, transmissions, anything. The paradox has only deepened since. The Kepler Space Telescope discovered that roughly 1 in 5 stars hosts a planet in the habitable zone where liquid water could exist. That gives us billions of candidates for life in our galaxy alone. Some of those stars are billions of years older than our own. If intelligence arose there, they would have had enormous head starts. A civilization only slightly more advanced than us could spread across the galaxy in a few million years, even traveling slower than light. Build self-replicating probes. Send them to nearby stars. Those probes build copies of themselves and continue spreading. Computer models show this colonization wave would sweep through the entire galaxy in roughly 1 million years. The Milky Way is over 13 billion years old. 1 million years is nothing on that timescale. If spacefaring civilizations exist, the galaxy should be saturated with them. Yet, we find no evidence. No ancient ruins on Mars. No mysterious structures on the Moon. No massive engineering projects visible in nearby star systems. Some scientists propose solutions to the paradox. Maybe interstellar travel is impossible due to physical limitations we do not understand. Maybe civilizations always destroy themselves before spreading. Maybe intelligent life is far rarer than we think, requiring such specific conditions that Earth is unique. The zoo hypothesis suggests advanced aliens know we exist but deliberately avoid contact, allowing us to develop naturally. This seems unlikely. It would require perfect coordination among thousands of civilizations over millions of years. One defector would break the silence. The dark forest theory is more sinister. Maybe civilizations stay hidden because the universe is hostile. Any species that announces its presence invites destruction from rivals. Everyone hides in the darkness, listening but never transmitting. This could explain the silence, but it requires us to believe that fear dominates every intelligent species. Perhaps the most disturbing possibility is that we are simply first. In a universe 13.8 billion years old, some civilization had to be first. Maybe it is us. We evolved early in cosmic history, before most stars capable of supporting life even formed. If true, we are witnessing a universe on the edge of becoming populated. Or we are witnessing the last moments before everything spreads too far apart to ever meet. Because while we search for alien neighbors, the neighbors we might have once had are moving beyond our reach. Imagine looking through a telescope and watching a galaxy fade from existence. You see it clearly one night, dimmer the next, gone within a few lifetimes. This will happen to most of the universe. The local group consists of roughly 80 galaxies bound together by gravity. Our Milky Way, the Andromeda Galaxy, the Triangular Galaxy, and dozens of smaller companions orbit a common center of mass. Gravity keeps us connected despite cosmic expansion. We are safe within this island. Everything else is leaving. The Virgo supercluster, a vast collection of galaxy groups including ours, contains approximately 47,000 galaxies. Most of them are already accelerating away faster than we can chase. Dark energy overpowers the gravitational attraction between distant groups. They drift apart, and that drift speeds up every second. In approximately 150 billion years, galaxies beyond our local group will have receded so far that their light can no longer reach us. The space between us expands faster than photons can cross it. Those galaxies will still exist, still shine, still possibly harbor life, but to us, they will be invisible, forever. Our descendants, if any exist, will inhabit a fundamentally different universe than we observe today. When they look through telescopes, they will see only the local group, no Andromeda Nebula showing us a neighboring galaxy, because Andromeda will have merged with the Milky Way by then. No distant spiral arms, no quasars, no cosmic web, just a small cluster of gravitationally bound galaxies surrounded by absolute darkness. They will have no evidence that billions of other galaxies ever existed. The expansion will have erased the proof. If they try to calculate cosmic history, they will conclude the universe is small, static, and local. All the discoveries we made, all the cosmology we confirmed, will become impossible for them to verify. This has already begun. Measurements from the Hubble Space Telescope show galaxies at the edge of the observable universe are receding at 98% the speed of light. Some are crossing the event horizon right now, disappearing from view while you read these words. The observable universe shrinks every moment. Think about the tragedy of this. Civilizations might exist in those distant galaxies, looking back at us, watching our light fade as we recede beyond their reach. We could be disappearing from someone else's sky right now, and we would never know. Communication becomes impossible when the space between us expands faster than signals can travel. The isolation is permanent. No future technology can overcome it. You cannot travel faster than light. Even if you could, the space itself is expanding. Attempting to reach a galaxy beyond the event horizon would be like running on a treadmill that accelerates faster than you can sprint. You would never arrive. We exist in a privileged moment. We can still observe a rich, populated universe filled with distant galaxies and cosmic structures. This window is closing. Every billion years, fewer galaxies remain visible. Eventually, only gravitationally bound structures will persist, and even those structures face an ending. You might think the observable universe grows as light from farther away finally reaches us. This was true for billions of years. It is no longer true. The observable universe is defined by how far light has traveled since the Big Bang. Light from galaxies 13 billion light-years away has been traveling toward us for 13 billion years. We see them as they were in the distant past. But here is the critical detail. We are seeing them at all because their light had time to reach us before expansion carried them too far. As dark energy accelerates expansion, there is a distance beyond which light emitted today will never reach us, ever. That boundary is shrinking. Galaxies that could have sent us signals a billion years ago cannot do so today. The expanding space between us has grown too fast. Current measurements place the edge of the observable universe at roughly 46 billion light-years away. Wait a few billion years, and that edge will be closer. Galaxies, sitting just inside the boundary, will cross to the outside, lost forever. The sphere of space we can observe is contracting. This seems impossible at first. How can the universe be expanding while our view of it shrinks? The answer lies in acceleration. If expansion were constant, light from any galaxy would eventually reach us, given enough time. But expansion is speeding up. Galaxies accelerate away faster and faster. Eventually, they move so fast that light cannot overcome the expanding space. Think of it like swimming upstream in a river. If the current is slow, you can make progress. If the current speeds up gradually, you struggle, but might still advance. But if the current accelerates continuously, eventually it flows faster than you can swim. You get swept backward no matter how hard you fight. The cosmic event horizon marks the point where recession velocity equals light speed. Anything beyond that horizon is permanently inaccessible. Observations from the Planck satellite and the Dark Energy Survey confirm this horizon exists and is moving toward us. Every second, more galaxies cross it. Scientists estimate that in roughly 100 trillion years, the observable universe will contain only the local group. Everything else will have vanished beyond reach. The night sky will show a few dozen galaxies at most. Dark, empty space will dominate every direction. But even that assumes we reach 100 trillion years, because the universe faces scenarios far more abrupt. Heat death awaits in the distant future, but other possibilities are much stranger. Imagine a universe where every star has burned out, every black hole has evaporated, and every particle sits motionless in absolute darkness at temperatures barely above absolute zero. This is heat death, and it is the most likely fate of everything. The second law of thermodynamics states that entropy always increases. Order becomes disorder. Energy spreads out evenly until nothing can do work anymore. A hot object and a cold object reach the same temperature. A concentrated fuel source burns and disperses. Eventually, everything reaches equilibrium. The universe is a closed system. Energy cannot escape. It can only spread out and dilute. Right now, energy is concentrated in stars, black holes, and hot gas clouds. Stars fuse hydrogen into helium, releasing light and heat. This process cannot continue forever. Hydrogen runs out. Stars die. Current estimates suggest star formation will cease in roughly 100 trillion years. All the available hydrogen and helium in galaxies will have been consumed or locked away in objects too cold to fuse. The last stars will flicker and fade. After that, only brown dwarfs, white dwarfs, neutron stars, and black holes will remain. But even those decay. White dwarfs radiate their remaining heat into space over unimaginable timescales. After 10 to the power of 15 years, they cool to near absolute zero, becoming black dwarfs, dark spheres of crystallized matter floating in emptiness. Neutron stars follow the same fate, cooling slowly until they match the background temperature of space. Black holes were once thought to be eternal. Then Stephen Hawking discovered they emit radiation through quantum effects. A black hole slowly loses mass, evaporating particle by particle. Smaller black holes evaporate faster. Supermassive black holes, like the one at the center of the Milky Way, will take roughly 10 to the power of 100 years to disappear completely. When they do, they vanish in a final burst of radiation, leaving nothing behind. After 10 to the power of 100 years, the universe will contain only isolated particles drifting through expanding darkness. Electrons, positrons, neutrinos, photons stretch to wavelengths longer than galaxies. The temperature will approach absolute zero. No energy gradients will exist to power any process. No structure, no chemistry, no life. This is heat death. Maximum entropy, complete equilibrium. Some physicists theorize that even protons might decay given enough time. If so, after 10 to the power of 40 years, matter itself will dissolve into radiation. The universe will be nothing but photons, and perhaps some exotic particles, all redshifted to near infinite wavelengths. At this point, time becomes meaningless. Nothing changes. Nothing can change. The universe reaches a static state that persists forever, an eternity of darkness, cold, and stillness. But we might not make it that far, because there are faster ways for the universe to end. 5 times more matter exists in the universe than all the stars, planets, gas, and dust combined. We cannot see it. We cannot touch it. We only know it is there because of what it does to everything else. Scientists call it dark matter, and its existence is confirmed beyond doubt. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster, a group of over 1,000 galaxies. He measured their velocities and calculated the mass needed to keep them bound together. The visible matter was not enough. The galaxies moved too fast. They should have flown apart billions of years ago. He proposed that invisible matter must exist, holding the cluster together through gravity. Most scientists ignored him for decades. Then, astronomer Vera Rubin studied rotation curves of galaxies in the 1970s. Stars at the edges of galaxies orbit faster than they should based on visible matter, much faster. The only explanation is that galaxies contain far more mass than we can see. That mass is dark matter. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation at all. The only way we detect it is through gravity. Dark matter pulls on normal matter, bending light from distant galaxies and shaping the cosmic web. Computer simulations of the universe require dark matter to match what we observe. Start with the conditions after the Big Bang and let gravity evolve the structure. Without dark matter, galaxies form too slowly and too small. With dark matter, the simulations produce the same large-scale patterns we measure. Galaxy clusters, filaments, voids, everything fits. Physicists have built incredibly sensitive detectors buried deep underground, shielded from cosmic rays and radiation. They wait for dark matter particles to collide with normal atoms. Decades of searching have produced no confirmed detections. Dark matter interacts so weakly with ordinary matter that it passes through everything like a ghost. What is dark matter made of? We do not know. The leading theory suggests weakly interacting massive particles, or WIMPs, but experiments have not found them. Other candidates include axions, sterile neutrinos, or even primordial black holes formed in the early universe. None have been confirmed. Here is the terrifying part. Dark matter shaped the universe. Without it, galaxies could not have formed. The gravity from dark matter pulled normal matter together after the Big Bang, creating the seeds that grew into stars and planets. You exist because dark matter exists. Yet we are fundamentally ignorant about what it is. Imagine learning that most of your body is made of an unknown substance you cannot see or feel. That is our situation with the universe. 85% of all matter is this mystery substance. Dark matter fills the space around you right now, passing through your body at this moment, and you cannot detect it. Dark energy is even stranger, making up 70% of the universe and actively tearing space apart. Together, dark matter and dark energy account for 95% of reality. We understand less than 5% of what exists. The universe is not just empty, it is fundamentally unknowable. And the unknowable might destroy everything in an instant. The vacuum of space might not be stable. We could be living in a false vacuum, a temporary state that could collapse at any moment, destroying the universe at the speed of light. Quantum field theory describes the universe as fields permeating all of space. These fields have energy levels, like a ball resting in a valley. The ball sits at the lowest point, the true vacuum, stable forever. But what if the ball is resting on a higher plateau, a false vacuum, with a deeper valley nearby? It looks stable until something knocks it over the edge. If the universe exists in a false vacuum, quantum fluctuations could trigger a collapse. A tiny region of space spontaneously transitions to the true vacuum state. This creates a bubble expanding at light speed. Everything the bubble touches is rewritten. The laws of physics change. Atoms might not form. Fundamental forces might have different strengths. Anything built from the old physics would disintegrate instantly. You would never see it coming. The bubble wall moves at light speed. No warning signal can outrun it. One moment you exist. The next, you and everything around you are erased and replaced with a fundamentally different reality. Scientists studying the Higgs boson at the Large Hadron Collider measured its mass very precisely. The value sits right on the boundary between stability and metastability. Calculations suggest the vacuum might be metastable, meaning it will eventually decay, but the timescale could be longer than the current age of the universe. Or it could happen tomorrow. The probability of false vacuum decay occurring in any given second is extraordinarily low, but across billions of years and trillions of cubic light-years of space, rare events become likely. Somewhere in the universe, a bubble might already be expanding. It could have started 10 billion light-years away and be racing toward us right now. We would have no way of knowing until it arrives. Some theories suggest cosmic inflation, the rapid expansion moments after the Big Bang, was driven by a false vacuum decay. The universe transitioned from one vacuum state to another, releasing enormous energy that drove expansion. If that happened once, it could happen again. The truly disturbing aspect is this: you cannot protect yourself. No technology could shield you from a change in the fundamental laws of physics. Bunkers, spaceships, even escaping to another galaxy would not help. The bubble catches everything at light speed. Most physicists consider false vacuum decay unlikely in our observable universe during the next billions of years. The calculations suggest stability, probably. But probably is not certain. The universe operates on quantum mechanics, where unlikely events happen constantly given enough time and space. We are gambling every second that the vacuum remains stable. So far, we have won. But there is another scenario just as destructive and possibly more imminent. Imagine dark energy growing stronger over time, not just maintaining constant acceleration, but actively increasing in power. If this happens, expansion will eventually accelerate so fast that it rips apart galaxies, stars, planets, and finally atoms themselves. Scientists call this the Big Rip, and some models of dark energy allow it. Right now, dark energy is relatively weak. It overpowers gravity only across vast cosmic distances. Galaxy clusters hold together. Stars remain intact. Atoms stay bound. But if dark energy is not constant, if it grows more powerful as the universe ages, everything changes. Physicists describe dark energy using something called the equation of state parameter. If this parameter equals -1, dark energy remains constant forever. If it is less than -1, dark energy strengthens over time. Current measurements suggest it is very close to -1, but not perfectly. There is uncertainty. If dark energy strengthens, the timeline to destruction is surprisingly short. Computer models show that if the parameter is even slightly below -1, the Big Rip could occur in as little as 22 billion years. That sounds distant, but it is barely longer than the current age of the universe. Here is how it unfolds. First, galaxy clusters tear apart. Galaxies that were gravitationally bound begin accelerating away from each other faster than gravity can hold them. Within a few million years, clusters disintegrate into individual galaxies drifting through space. Then galaxies themselves shred. Stars at the edges accelerate away faster than orbital velocity. The spiral arms unwind. The galactic core loses its grip. Stars scatter into the void. About 3 months before the final moment, the solar system breaks apart. Planets rip away from their orbits. Earth flies off into darkness. About 30 minutes before the end, Earth itself explodes. The molecular bonds holding rock and metal together cannot withstand the expansion of space. The planet tears into fragments. Then those fragments tear apart into atoms. Finally, in the last fraction of a second, atoms disintegrate. Electrons rip away from nuclei. Nuclei themselves split apart. Quarks separate. Space expands so fast that no force can hold anything together. The universe tears itself to pieces at the smallest possible scale. Then nothing, or possibly a new Big Bang, triggering a new universe with different properties. No one knows. Current data suggests the Big Rip is unlikely. Most measurements favor a constant dark energy that leads to heat death instead. But the uncertainty remains. We do not fully understand dark energy. Its nature, its origin, its future behavior are all mysteries. If the equation of state parameter is wrong by even a small amount, if dark energy is slightly stronger than we think, the timescale to catastrophic collapse shortens dramatically. We could have billions of years or just millions. And while we debate which ending awaits, some light has already become unreachable. There are galaxies shining right now whose light will never arrive, ever. The space between us is expanding too fast. When you look at a distant galaxy, you are seeing its past. Light takes time to travel. A galaxy 1 billion light-years away appears as it was 1 billion years ago. The farther you look, the further back in time you see. This seems to suggest we could eventually see everything if we wait long enough. That assumption is wrong. Light travels at approximately 186,000 miles per second. Nothing in the universe moves faster. But space itself can expand faster than light can cross it. This is not a violation of relativity because space is not moving through space. Space is stretching. Imagine 2 points in space, separated by a vast distance. Light leaves one point, traveling toward the other. But as the light travels, space expands. The distance between the 2 points increases. If space expands faster than the light can close the gap, the light never arrives. It keeps traveling, making progress locally, but falling further behind globally. Current measurements show that galaxies roughly 16 billion light-years away are receding at the speed of light. Galaxies farther than that are receding faster than light. Their light moves toward us, but the space between us grows faster. The photons make no net progress. They are trapped, forever journeying but never arriving. This creates a cosmic horizon, an edge beyond which we can never observe, not because the light has not had time to reach us yet, but because it will never reach us. The expansion of space prevents it. Think about what this means for civilizations in those galaxies. If they turned all their stars into a massive beacon and aimed it directly at Earth, we would never see it. If they sent radio signals, wrote messages in pulsars, or built megastructures visible across billions of light years, we would remain ignorant. The signal exists, traveling through space, but expansion swallows it. The reverse is also true. Any light we emit today will never reach galaxies beyond the horizon. We are invisible to them, and they are invisible to us. Communication is impossible. Contact is impossible. Even if both civilizations survive trillions of years, the gap between them only widens. The observable universe is not limited by how far light has traveled. It is limited by how fast space expands, and that expansion is accelerating. Galaxies sitting just inside the horizon today will cross to the outside in the future. The pool of observable galaxies shrinks continuously. Astronomers estimate we have already lost contact with roughly 80% of the galaxies that exist. Their light will never reach us. We are seeing a small, dwindling fraction of reality, and the fraction we can see is isolated in an ocean of darkness. Stand at the shore and look across the ocean. You see water in every direction, stretching to the horizon. Now imagine that ocean is darkness, and the shore you stand on is shrinking. That is our cosmic situation. The local group, our island in space, contains roughly 80 galaxies gravitationally bound together. The Milky Way, Andromeda, Triangulum, and dozens of dwarf galaxies orbit a common center. Gravity keeps us connected. We are safe from cosmic expansion, at least for now. But look beyond the local group, and you see galaxies accelerating away in every direction. The Virgo supercluster, a collection of groups including ours, is already stretching apart. Measurements from the Hubble Space Telescope show that distant members of the supercluster are receding faster than gravity can resist. Dark energy wins. In roughly 100 billion years, every galaxy outside the local group will have crossed the cosmic event horizon. They will still exist, but their light can no longer reach us. To our descendants, if any survive, the universe will appear as a small cluster, surrounded by infinite darkness. This isolation is absolute. No technology can overcome it. You cannot build a faster-than-light drive because physics forbids it. Even if you could, the space itself expands. You would be like a swimmer fighting an accelerating current. No matter how fast you swim, the current grows faster. The local group is an island, but even islands erode. In approximately 4 billion years, the Milky Way and Andromeda will collide. Gravity will pull them together despite cosmic expansion. They will merge into a single, massive elliptical galaxy. Smaller galaxies in the group will either merge as well or orbit the combined giant. After the merger, the new galaxy will contain roughly 1 trillion stars. It will be the only major galaxy visible in the night sky. Everything else will have vanished beyond the horizon. Astronomers living in that era will have no evidence that other galaxies ever existed. They will conclude the universe is small, static, and consists solely of their home galaxy. All the cosmology we have discovered will be lost. Future scientists will not be able to confirm the Big Bang because the cosmic microwave background will have redshifted into undetectability. They will not see distant galaxies showing cosmic expansion. The evidence will be gone. Some physicists wonder if we are already in that position. Maybe the universe is far larger and more complex than we can observe. Maybe evidence of earlier cosmic epochs has already been erased by expansion. We could be the future civilization, looking at a fraction of reality and mistakenly thinking we see it all. The darkness surrounding our island is not empty space waiting to be explored. It is space expanding away from us, faster than we can chase. The ocean grows wider every second. The shore shrinks beneath our feet. And inside this darkness, the void itself seethes with activity we barely understand. The void is not empty. It is alive with particles that appear and disappear in fractions of a second. Quantum mechanics reveals that empty space is not truly empty. Uncertainty principle demands that energy cannot remain perfectly zero for any length of time. Instead, energy fluctuates randomly. For incredibly brief moments, particle-antiparticle pairs pop into existence from nothing. An electron and a positron appear together, exist for a tiny fraction of a second, then annihilate back into the vacuum. These are called virtual particles, and their existence is confirmed by multiple experiments. The Casimir effect demonstrates their reality. Place two metal plates very close together in a vacuum. Virtual particles appear in the space outside the plates and between them, but the gap between the plates is too small for certain wavelengths of particles to exist there. More virtual particles appear outside than inside. This creates a tiny pressure pushing the plates together. Scientists measured this pressure. The effect is real. Virtual particles exist. The vacuum seethes with them constantly. Electrons, quarks, photons, every type of particle blinks in and out of existence. Most exist for such short times that they cannot interact with anything. They borrow energy from the vacuum, exist briefly, then repay that energy when they annihilate. This might sound irrelevant, but it has massive consequences. Virtual particles contribute to the vacuum energy of space. Some physicists believe dark energy might be related to vacuum energy. If so, every cubic meter of empty space contains energy pushing space apart. The more space exists, the more energy exists, driving expansion faster. Black holes interact with virtual particles in strange ways. Stephen Hawking discovered that near the event horizon of a black hole, virtual particles can become real. One particle falls into the black hole, while the other escapes into space. From an outside perspective, the black hole emits radiation. This Hawking radiation slowly drains the black hole's mass. The vacuum is also filled with quantum fields permeating all of space. The Higgs field gives particles mass. The electromagnetic field allows light to propagate. These fields have ground states, minimum energy levels they cannot drop below. That minimum energy is not zero. It contributes to vacuum energy. Calculations trying to predict vacuum energy from quantum mechanics produce a number 120 orders of magnitude too large compared to what we observe. This is called the cosmological constant problem, and it is one of the biggest mysteries in physics. The vacuum should have far more energy than it does. Why is it so small? No one knows. But we are fortunate it is small. If vacuum energy were as large as quantum mechanics predicts, space would expand so fast that galaxies, stars, and atoms could never form. The universe would rip itself apart instantly. The void is not absence. It is a churning sea of virtual particles, quantum fields, and energy we do not understand. Dark energy might emerge from this quantum foam, or it might be something else entirely, a force woven into the fabric of reality itself. Either way, the void is winning. It expands, it separates, it erases structure, and what comes after these 17 truths is even stranger. Matter might not be permanent. The atoms making up your body, this planet, every star in the sky could be slowly decaying into radiation. Given enough time, everything solid might simply vanish. Protons are the building blocks of atomic nuclei. Every element on the periodic table depends on them. Hydrogen has 1 proton. Carbon has 6. Iron has 26. We thought protons were stable, eternal. Recent physics suggests otherwise. Grand unified theories predict that protons decay over extraordinarily long timescales. The estimated half-life is roughly 10 to the power of 34 years. That number is almost incomprehensible. The universe is only 13.8 billion years old. Write that as 10 to the power of 10 years. Proton decay takes 10 trillion times longer. Yet given infinite time, all protons will decay. An atom of iron sitting in space will eventually see one of its protons split apart, transforming into lighter particles and gamma rays. The atom becomes something else. Wait long enough and another proton decays. Eventually, nothing remains but photons and perhaps some exotic particles. Physicists have built detectors containing thousands of tons of ultra-pure water, surrounded by sensors watching for the flash of light that would signal proton decay. They have watched for decades. So far, no confirmed detection. If proton decay happens, it occurs so rarely that we have not yet seen it. But absence of evidence is not evidence of absence. The timescales involved are so vast that we would not expect to see decay in human lifetimes. Our experiments simply set lower bounds on the proton lifetime. It must be longer than 10 to the power of 34 years, or we would have detected it already. What does this mean for the far future? After the last star dies, after black holes evaporate, the universe will contain mainly protons locked in dead remnants. Black dwarfs, neutron stars, frozen planets. These objects will drift through expanding darkness for unimaginable ages. Then proton decay begins claiming them. One atom at a time, the solid matter dissolves into radiation. A black dwarf, a sphere of crystallized carbon and oxygen, slowly transforms into photons. After 10 to the power of 40 years, the decay process will have erased most baryonic matter. The universe will contain only photons, neutrinos, electrons, and perhaps some unknown stable particles. At that point, even calling it a universe seems wrong. No structure remains, no chemistry, no possibility of complexity or change. Just isolated particles, drifting through exponentially expanding space, growing more distant from each other every moment. Some theories suggest proton decay might not happen at all. Protons could be perfectly stable, lasting forever. But if so, matter persists only as isolated particles in a cold, dark, ever-expanding void. The outcome is not much better. Either way, the material universe has an expiration date. Everything solid will eventually disappear, leaving only radiation stretched across infinite distances, and long before protons decay, another ending arrives. There will come a night when the final star burns out, and darkness claims the universe forever. Star formation requires hydrogen gas. Gravity collapses clouds of hydrogen until pressure and temperature ignite fusion. The star begins burning, converting hydrogen into helium, releasing energy that lights up space. This process has continued for over 13 billion years. It will not continue forever. Hydrogen is finite. Every star that forms locks some of it away. Massive stars burn through their fuel in millions of years, then explode as supernovae, scattering heavy elements but consuming hydrogen. Smaller stars burn slower, lasting billions or even trillions of years, but they too eventually exhaust their fuel. New stars form from recycled material, gas expelled from dying stars, but each cycle locks away more matter in compact remnants. White dwarfs, neutron stars, black holes. These objects remove hydrogen from the available supply. Over time, less fuel remains for new star formation. Astrophysicists modeling galactic evolution calculate that star formation will peak and then decline. The Milky Way is already past its peak.